Good morning, all. Thank you for joining us in today's webinar, Mastering PID Control Best Practice for Consistency and Efficiency. I'm Vera from Control Station. I work in the marketing department, and I will be hosting this webinar with Dennis and Brett from Control Station. And just before we start, feel free to input your questions and comments anytime you want. Here in the GoToWebinar panel, there is a tab named questions, and you can just type your questions, or you can send by email to us and we will be happy to answer. Our presenters is Dennis and Brett. Dennis is our company's president and lead strategy. He took over Control Station in 2004, moving it from campus of the University of Connecticut and repositioning the company as a marketing leading provider of process optimization solutions. And Brett leads our research and development effort as director. It was Brett who conceived our non-steady state modeling innovation, which eliminates the need for steady state condition prior to performing a bump test. His role in today's webinar is very appropriate. And about Control Station, for those who are new to Control Station, we've been driving innovation in process control since the 80s. And today we are proud to support customers all around the world, including many of the leading manufacturers across the process industries.
Good morning, everyone. Thank you for joining us. Dennis Nash here of Control Station. For today's webinar, we will be covering, as Vera shared, best practices for mastering PID control, with a focus on efficiency and consistency. So we'll start with why PID remains relevant in today's modern industrial settings. We'll then pivot to a structured approach to utilizing PID in modeling and tuning controllers across your enterprise. But we'll then hope to focus on approaches that permit a sustained optimization effort, important for efficiency and consistency to have a plan. We'll conclude with a case study that I believe Brett had a hand in earlier in his career, and look forward to some Q&A from you, the audience. Vera, next slide. As we like to conduct here with our webinars, we begin with a quick poll question, seeking a bit of understanding of who's joined us today. And this question: how often do you model and tune PIDs at your facility? There's a range of options. Please feel free to select one, and we'll wait just a few moments for the poll to be responded to before Brett and I begin today's webinar. Again, the idea here is to understand who's in the audience and what the association is with PID tuning, so that the remarks Brett and I offer can be more relevant.
Yeah, I'm interested in seeing what's going to happen with this one as well. Usually we get a good spread, but it'll be interesting to see who we're talking to. I think I have something for everyone. But
yeah, whether they're tuning all the time or not at all, it will help us to understand again how to cater our thoughts with today's presentation.
I'm going to share the results here.
Oh, fantastic.
Yeah, that close.
Like that distribution, you know, I remarked that even those who have no experience tuning PIDs, this helps us to deliver today's presentation in a more thoughtful fashion. But it's not unusual, Brett, for us to see this type of spread, is it?
No, not at all. I think that it's pretty straightforward, and frequently is pretty common, right? If you're tuning loops every day, then you probably, you know, it's something that you do every 3 or 4 months, and it's kind of difficult sometimes to pick back up where you left off in terms of understanding. But then there are the larger facilities where somebody just does it every day because there's 1,000 control loops. Yeah, this is pretty standard. And welcome to the never people. Hopefully we can give you a couple tips that'll move you from never to occasionally.
Brilliant. So I'd offered in the agenda that we would begin with why PID remains relevant in today's industrial automation settings. The importance of the PID, as this graphic seeks to demonstrate, is that the PID controller remains the primary workhorse for industrial controls. And whether you're from chemicals or food and beverage or other of the industries that are shown here, you can see high percentages of use of the PID. And what is offered there on the margin to the right is indication of the importance in terms of the economic impact that PID and applying effective, efficient, and consistent practices can achieve, whether that's improving utilization of production inputs, reducing downtime, or otherwise. Quite a wide range of benefits. Brent, any thoughts on this slide?
Yeah, this is pretty much similar to what we're doing. And the good thing about it, as we'll see here in a second, is that you can, without even a system, you can still elicit some benefits with just putting eyes on the loop and tuning it to get some of this, but really to kind of get to that last inch. It's really helpful to have kind of more procedural stuff in place to make sure that you can really nail it down and get every last squeeze every last drop of efficiency out of your loops.
Our next slide.
So that being said, one of the benefits of PID is that it's kind of easy to fiddle around and get something that at least is safe, right? The first thing that the regulatory control system is there for is to make sure that things don't run away, right? If everything's in manual, you're going to be running far from that plant. And so just having the PID in place is of benefit for safety. But then, if things are oscillating or whatever, you might have your first encounter with the PID loop and you can discover, oh, when I change this number, it gets better. When I change this number, it gets worse. And you can kind of work your way towards a solution. And no shame in that, right? That's a really it's great that the PID can do that. And with limited training, you can find your way to a good set of tuning parameters. It can, it's not awesome because are those the best tuning parameters? You don't know. There's kind of a black box situation to it. Different people will do it, might have a different, experience level. They may have different styles of tuning. They may do different things. And so you might not necessarily get the same improvement across the board, depending on who's doing it, their control level. And also, one of the challenges with manual tuning is it's a pain in the butt, right? It just takes forever. And so there are certain things that you just decide to leave on the table because you have bigger fish to fry. I can't spend all morning tuning this thing. And so as a result, you don't tend to go back to the loop and really try to optimize it. So you don't get to handle things like process variability, right? Maybe the process is very different in the summer and the winter, but you have numbers that are close enough. Or maybe startup's different than runtime. Again, if you're tuning it manually, you probably don't want to spend the time to go through those things. So process variability is a problem. And as I alluded to earlier, this lack of structure will cause just inconsistency between, if your controls guru leaves the plant, now you're kind of out in a lurch, right? You have difficulties there. So this lack of documentation, this lack of structure is a recipe for kind of a tenuous relationship with your loops. You have a safe plant, which is great, but you really have a hard time keeping and maintaining these performance gains that you want.
I might add, with our background starting on campus at University of Connecticut, we developed a curriculum where the emphasis of that curriculum was to delineate a methodical process by which, whether tuning manually or with the help of technology, you could make informed decisions throughout that method to make sure that you got to a consistent and efficient outcome that would ultimately improve control. Touching on this, trying to demystify the black art of PID, reduce variability in the process, but provide that structure and ultimately the documentation, things that Brett and I will cover throughout this webinar this morning. So Vera, could you advance to the next slide, please? So as I was suggesting, this approach that Control Station and other vendors, whether they be on the educational side or the technology side, the objective is to develop a process which is well defined, one that can be stepped through in methodical fashion that provides the corresponding documentation. But of course, there's that last element, which is the training. Just using a tool without an understanding or appreciation for what good control looks like, what an effective model fit should address. Those are all important aspects of training, which ultimately all coalesce around this idea of repeatability. And repeatability is what we're looking to approach or achieve with tuning, so that we can have consistent results, so that we can have an efficient process. Brett, can you offer some additional remarks on that?
That's really the name of the game, is being able to get the same thing out of different people at different times and quickly is really the name of the game when it comes to having a procedure for tuning. If it's not a headache and it's not something that's takes a long time, it's something you're going to want to do more often. It's something that you're going to be able to see more benefits from. And yeah, that would be what I would say. That's been my experience anyway.
Eric, could you advance to the next slide, please? So we've been fortunate this year to have a fantastic roster of webinars that have been co-hosted by leaders from across the process industries. This next month, October, we will be joined by Lindsay Wilcox of Seek. As many in today's audience know, Seek has been a thought leader in process analytics. They've a toolbox which allows production staff, engineering staff to pinpoint major sources of variability and to track them to proactively maintain optimal control. So looking forward to Lindsay's joining us as we tackle this idea of demystifying root cause analysis. Hopefully all of you will have a chance to join us next month. Please feel free to use the QR code shown on your screen to register for that webinar. Vera, if you'll advance.
Yeah, it's another poll, so just launching here.
Great. Again, these polls help us to understand what your experience is with modeling and tuning. And more specifically, in this case, we previously asked about the frequency or the exposure that the audience has had with tuning PIDs. Here we're looking more specifically at the approach, whether it is manual, whether it is using trends from the HMI or a third-party software, maybe something built into the DCS. Of course, option number 5, not applicable, not at all.
I have seen all of these. My favorite is the intuition, because there are definitely people out there that can crush it, like with tunings. That's what it's amazing knowledge when somebody who can intuit the tuning parameters can show up and do it, and they usually do a great job. The challenge there is just, if they leave, if they retire, it still takes them a while sometimes, a couple guesses and stuff like that. But yeah, I've seen all of these, and they all have their strengths and weaknesses, except for maybe not applicable, which is just all weakness. But yeah, it'll be really cool to see how people respond to this one.
Sharing the results.
Thank you, Vera. Again, interesting. Our NA group down to 7% from those who hadn't tuned. So it'd be interesting to understand what that NA represents. Third-party software, manual calculations, intuition? It seems in all of the above, Brett, almost a
Yeah,
wide,
yeah.
even spread across the top 4.
Yep. I like that auto tune is a little bit further back. Auto tune's a bit tricky sometimes. It's I prefer an informed user than auto tune, but if that's what you got and it gives you results, then it's hard to argue with limited success, right? It's better than absolutely nothing, or if it does a good job for you, that's also fantastic. But yes, also hats off to the people who are doing manual calculations with trends. That's not super easy, but it's rigorous, which is admirable.
Sarah, let's advance.
Sure.
Great. So when we think about modeling and tuning with the objective of consistency, with the objective of efficiency, we like to start with understanding the process itself. And as represented on the screen in this slide, a simple place to start, understanding your process, is whether or not you have an integrating or a non-integrating process. That will influence the approach that you take, whether from the perspective of the bump test, the type of bump test, the size of the bump test, other attributes within your process, the noise level, interaction, etc., that will influence the dynamics of the process. All of those components will have a direct impact on the approach that's applied. And Brett, I think I'll turn it over to you for some additional context on this. What's your attack on this?
I mean, the analogy I usually use when I'm teaching this is that, if you want to try to design the cruise control for a car, and you really have to know what kind of car you're driving, you can't just, go in blind. And so the first thing to really do is kind of get the lay of the land. And then with that, whether it be graphically or just, manually getting a look at the process to kind of understand what's going on is really the first thing. If you start futzing around with tuning parameters without even knowing what you're connected to, you're in for a long day. And so here, obviously, we're talking about the overall shape of the process, be it on the left, you're looking at something like temperature or flow. On the right, you're looking at something like level generally, although wave feeders and things like that may also exhibit that kind of behavior. But, so that's kind of the overarching understanding. But then just the other things are really important. I would also add that understanding what you're after, which I think we're going to talk about here in a minute, is also an important thing to understand. But if you can start with some knowledge before reaching the tuning process, you're going to be well ahead of the game and not have to double back a lot during your process.
Sarah, let's proceed.
So yeah, as I alluded to here, the first step would be kind of the first 2 steps there, right? Your control objective is kind of what I was alluding to there in the last slide, is that you want to know your process, but you also want to know what you're after. A lot of times people will see a PID controller and they want that level to hold super tight to the set point because that line looks great. But if you got a surge tank, that is not what you want, because if the level is held perfectly solid, any disturbance that comes into that tank is going to be immediately passed out the bottom. So essentially you've turned that tank into a fat spot in the pipe. You want to, and as we will see here a little bit later, we are going to be talking about that exact process here in a little bit. We want to be able to adjust things, but there are other things with the controller objective. Do I want this furnace to heat up quickly, or will that damage the furnace? Do we need to adjust our control styles, etc.? So step 1 would be to follow that. Then we're going to be looking at doing specific kinds of tests, deciding which tests we want to do based on some rigorous criteria, then doing some sort of mathematical analysis. We have the people who are graphically analyzing doing this process, but there is other methods with software. And then lastly, when you have that understanding, we can then use that understanding to say, oh, okay, so the first 3 steps are just to figure out kind of what we're dealing with. And then the last part, getting the tuning parameters, is like a layup. Once you know what you're dealing with, oh, okay, all you have to do is this then. And so it becomes much more methodical. There's less guesswork in the tuning step. It's really about understanding the process, which can be done repeatedly by different people and reliably, and then we can just do a layup into the tuning correlations to get the actual tuning parameters. Anything you'd like to add there, Dennis?
I think you nailed it, Brett. Thank you. Fundamentally, starting with what the ultimate objective is drives the process. That's why it's first or step number one. Without that clear understanding of the process and ultimately what you're trying to achieve, I thought your suggestion of the surge tank, you're not tuning the surge tank for precise control, but rather to handle the disturbances. And so by beginning with that controls objective, you're able to lay out the next steps of your process, as we've been attempting to express this morning, so that you can achieve that efficiency and consistency in control. Vera, if you'll advance to the next slide. So we have a long history here at Control Station. I guess we're coming up on 45 years or something of that nature with our involvement with PID. And whether or not you're using software or performing the tests and analysis manually, the goal is to follow a procedure that is simple, right? Something that is easy to understand for the average process engineer or even technician operators, so that you can achieve repeatability in the process. What Brett will cover shortly is that when you're applying tuning software, is that you're able to refine the analysis, because there are things that the software can pick up in terms of its assessment of the process data that are typically lost or invisible to the human eye. And some of the analysis, whether it be in the form of R-squared modeling results or other details, they're helpful in applying this repeatable process. As shared earlier in the remarks, this idea of bump testing, how big, how long, where is it relative to the noise band, what type, is it a step, is it a doublet, is it a PRBS? These are important decisions that tuning software can facilitate, providing that structured, repeatable process, and ultimately making the process simpler by guiding users through that. One of the benefits of software versus manual tuning. But ultimately, validation and documentation is a key outcome, because software will often provide a paper trail of all of the decisions that are made through a tuning process, so that you have information with which to go back and reflect on and find any adjustments that might have resulted in improved performance. But you have that paper trail to reflect on. Ultimately, where PID tuning software tends to provide its benefit is on the ROI. It's cutting down the time that it takes to tune or model and tune an individual PID. It takes away the time needed to perform the correlation analysis. It certainly reduces the time in terms of the number of bump tests that are often involved. And as the individual who's done the most tuning here on today's webinar, Brett, what thoughts might you share relative to this particular structured approach to PID?
Yeah, I mean, I'll also add one more thing. We'll get to it in a second, but it also takes away the time it takes for someone to go from not knowing about PID and becoming a guru by doing manual tuning. That one is a long one as well. But yeah, I mean, this really, you know, maybe I'm lazy, but I really like it when there's a program that makes things faster for me. Also, you know, documentation and things like that. It seems like a no-brainer for me, but maybe I'm a little biased. I think that it really, if you have the tool, it's like, you know, you can drive a hammer, you can drive a nail with your forehead, or you can use a hammer. And I prefer the second option.
I don't think the word is lazy, Brett. I think it's impatient. Be kinder to yourself. And I think that's actually a relevant remark for the audience, that we are all increasingly busy, and we are all fighting for time. And if there are approaches or methods, whether they be manual or tools that automate your procedure for making good, well-informed decisions, that's a boon for you, that's a boon for your business. Vera, could you advance to the next slide, please?
Right. So we talked about this a little bit going in terms of the time and things like that. But yes, the manual tuning guru is awesome until it isn't anymore. Having a kind of a contingency plan or a migration plan for employee turnover, et cetera, is more difficult in that setup. So having a procedure in place is really going to be the way that you can keep yourself in tip-top shape, as we could say. So that means training new people, okay, making sure that people know the methodology that you're using, know the tools that you're using, have a way to understand any kind of KPIs you might be using to track performance. So just then once you have the understanding, having a way to record what you've done and things along those ways, having some sort of method in place so that you can make sure that everybody knows what the score is, and then finally having a method or a procedure in place to get it done before it needs to be done. Right. A lot of, the 2 a.m. call from the operators is not a good one, right? Better to do it on a regular interval, the same way you would replace a valve before it fails, just on a regular PM schedule. Similar deal, right? Better to do it consistently on a schedule. And that's really the way to kind of get the long-term benefits out of this. Dennis, anything else?
Yeah, to jump in on those thoughts, Brett. I like that the first graphic, the training. I think fundamentally this is where it all begins. It's the understanding of process dynamic behavior. It's the understanding of a methodology where a process can be applied for consistent and efficient results, right? Which is today's webinar. But just underscoring that, I also would like to remark that this slide, we've shown it as 3 separate columns, but we could have just as easily and maybe more effectively suggested as a circle, a virtuous cycle where the training leading to knowledge transfer and regular tuning across the enterprise, maintaining effective control, but also continually optimizing. The reverse of that, however, the vicious cycle without effective tuning, without regular transfer of knowledge from the experienced veteran down to the new greenhorn, without routine tuning of loops, the facility's process control will ultimately fold. It will degrade, and that will have a negative impact on productivity, on profitability. So just some remarks from the business side of PID. Sarah, if you'll advance the next slide, please. Again, well, here we are showing that cycle, but rather than the vicious cycle I was talking about or the virtuous cycle to begin with, here we're showing a 6-step repeatable process. Technology allows you to very easily find the PID that you're looking for rather than culling through the HMI or data from your historian. Again, technology can make it very simple to identify the loop, to perform the bump test. Brett, you touched on that earlier. Using it to understand where the noise band is, escape the noise band with your bump, whether it's, again, a doublet or a step or otherwise. Finding the model and calculating the model attributes so that you can fine tune it to get to those tuning parameters that are ideal, testing it and documenting. Again, this is an important approach that most third-party technologies apply, but these are the same elements that correspond to most manual approaches. Brett, why don't you share some of your perspective, again, as the individual who's tuned lots of loops, lots of different ways.
The graphical people will be following this loop. Unfortunately, the intuition people will be going back and forth between steps 2 and 4 many times. Fewer times as they get more experience, but there's still this kind of like, change the numbers, see how it looks, change the numbers, see how it looks, on and on and on. But yes, I prefer the do the loop, get it done, move on to the next one. Yeah, that would be my feedback on that one. Having a system means that you're done at some point, which is something that I really enjoy.
Well, if I could just add a final remark here on this particular graphic, there in the middle, you've got what is intended to represent operations, engineering, and maintenance. This methodology is essential for all of those groups and their ability to maintain effective, safe operation within the plant. So there's quite a bit of benefit to what we're covering this morning here during the presentation. Vera, if you'll take us to the next slide, please.
Yeah, let's have some fun. So as let's go through the process of what we've been talking about here. Have a kind of a procedural how we would kind of go through this process by tuning, in this case, a surge tank level. Convenient that I mentioned that earlier as being a difficult process. Level is routinely listed as one of the more difficult level types to tune, and so I felt that we could kind of go through this and maybe explain a little bit about why it's so hard. So unlike some other processes, where you kind of have the self-regulating behavior, where for every value of the output, you kind of settle out at some new value of the PID input. This type of process is a little bit different. So this process, you're controlling the rate of change of the process variable. So you have a balance point where if you have the output at that point, you're flat. If you deviate from that balance point, you're then changing the rate of control up or down. And that can lead to some challenging behavior when you're trying to do bump tests or things of that nature. So for example, can we advance to the next slide, please, Vera? So if I were to, So if I were to increase or open the valve, that would increase the flow out of the tank, and that would drain the tank completely. This is kind of a challenging dynamic to tune manually, because generally, or especially using these graphical methods, right? Because generally what's going to happen is you're going to want to do a test where you can see what's going on. Well, it's kind of difficult to hold the loop flat. It's kind of difficult to, safely bump this guy to make sure that you stay within safe parameters. And so generally you're faced with kind of not really bumping it, just changing the number. So manual can be a bit of a challenge when you're trying to do manual tuning and things like that for this process. The problem is if you want to keep it in automatic and do a bump test, you're kind of faced with another challenge. If you can, Vera, please go to the next slide. So this is kind of a double, right? This shows that it's difficult to, kind of get good, you can't really bump the process kind of safely. It shows a couple things here. So the integrating processes are just generally difficult to control naturally with PID control. What you'll see here is that you may notice that no matter where I move on this grid, so I have more integral action, less integral action, more proportional action, less proportional action, and derivative would not change this kind of construct. Just by math, if you have an integrating process and you have an integral term, you will have, we can see here, overshoot in every single spot. There's no way to change that. There's no way to get around it. Just if you have integral, you will have overshoot with your set point changes, and that can be daunting. I've shown this slide dozens, if not hundreds of times in classes, and with pretty much regularity, you'll get like a forehead smack because people have spent weeks trying to get rid of this overshoot, and it's just not possible. Okay, so that's one of the traps you could fall with manual tuning, is that you'll never know if you're done. You'll never know if you quite get to that best case that you want, because with tuning and integrating level style control, you're really just trying to find the best spot in a bad situation. So maybe you want, I don't know, middle left. That looks pretty good. Maybe that's what you want. Or maybe you're looking for a more surgy kind of style response. Maybe you're looking for lower right. That would be covered in our first step, knowing what you want. But it can be really difficult if you're manually tuning to know if you really got there, or if there's some magical spot in this plot that you haven't seen yet. Any thoughts on this, Dennis?
No, I think you've offered a great perspective on this map and where it can take you if you understand what you're trying to achieve from a PID control standpoint. So
great.
Vera, I wanted to advance to the next slide.
Please. So, you know, using the process that we've discovered makes things a little bit easier. So we can talk, well, let's talk a little bit about, this is the busiest slide, right? I want to get all the busy stuff out of the way. If we're talking about tuning a surge tank, we can talk about going through the process. As we mentioned, the first step is going to be figuring out what you want. And I alluded to that being very important earlier, because a lot of times people just want to have that flat level. And that's just not what you want with a surge tank, right? The goal is to drift as much as possible to absorb the flow and have a constant output without tripping your high or low limits, right? That's the goal with the surge tank. That's number one. Number two, I kind of want to give you a little extra thing here, where if you have a process model of an integrating process, while this math looks a little funky, not too hard, it's based on 2 parameters and a adjustable closed loop time constant. You can very easily dial in exactly the type of response you want, which really helps, you know, with the whole knowing when you're done, knowing you get good values, etc. The closed loop time constant is an adjustable parameter that lets you specify how fast or how slow you want your tunings to be. Just, you know what kind of car you're driving, okay. How fast or slow do you want to drive it? These tuning correlations will let you do that. The goal here is that this tau c closed loop time constant should be large, which means it takes a long time, but not too large, right? You want it to be large enough that it will let you swing, but not so large that it will let you swing through a high or low. Okay, so the idea here for this tank that we were talking about before is, or any tank, right? If you know that when a disturbance hits, it will take you 5 minutes to hit an alarm, you want to make sure that you're less than 5 minutes. It's pretty standard. So let's see how that would work in this case. Okay, let's give you some numbers and some math. All right, so here we have a surge tank. Okay, it has a wild stream, and in practice, usually this is multiple streams, but they can usually be approximated to have a single stream. Let's assume that this tank is a 1,000-liter tank, that we generally stay in the middle, and then we have alarms 10% above and below that. So we can just do some quick math to be like, okay, tank volume is 100 liters. So in this case, we've looked at historical data, and we can see the largest fluctuation from the inlet flow is 2 liters per minute. Okay, we know that our surge space, you know, we have 10% of 100 above and below. That means we have 10 liters of available space to go up or down. And we know that our fluctuations can be 2 liters per minute. 10 divided by 2 means that we got to get this thing around in less than 5 minutes, or we're going to get an alarm, and that's not good for anybody. Okay, so if you're presented with this in a manual condition, that's kind of a challenge. Okay, it's kind of difficult to be playing with the numbers because you're not sure if you got it just right. Okay, but if you can generate a process model using manual methods or with software, which can be done by anybody who's trained, then it's pretty trivial, because, can you advance to the next slide, please, Vera? It turns out that with these tuning correlations, okay, this tau c, which is our closed loop time constant, it's very convenient that that tau c also corresponds with the arrest time of an integrating loop on a just standard hit, right? So if this guy gets hit with a disturbance of a given size, the closed loop time constant will tell you how long it's going to take for that controller to bring it around. Okay, so in this case, that's perfect, because you can just be like, well, okay, 5 minutes, I'll just make the tau C, maybe 4 minutes, 4.5 minutes, right? Just to make sure that that guy comes around before we trim the alarm. And then you can just say, done, on to the next one. Don't need to worry that I got the wrong numbers, right numbers. Did I, staying up at night being like, well, maybe when I tested it, it wasn't the things we had before, and you have a simple, straightforward process that's way easier to execute just by anybody day to day, month to month. And that's really the benefit there, okay? I hope what you're seeing here is that this is just one of many ways, many processes where this would become beneficial, okay? This is not the only way that this works, is that any loop that you approach has very similar process. You approach something that used to be difficult, and now you go through a simple set of steps, and now you have a set of tuning parameters, which opens up the world, frankly. Right now, oh no, I need a set of tuning parameters for high speed, low speed. Okay, right? It used to be a pain in the butt because you were only at low speed for a little while. Okay, now you can do a model there and you're done. That kind of thing. I could list many more examples, and if you have questions at the end, I can kind of flesh that out a little bit more. But that's basically an example of how this process would be laid out. Dennis, do you think I missed anything? Anything to add there?
No, I think you did a great job of expressing the rationale, the benefit of the process. And I think it shouldn't be lost on the audience, the idea of taking a complex challenge, tuning PID loops for improved performance, and methods, software or otherwise, break it down into its component parts, which are simpler challenges to address. And so by taking the complexity of PID control and breaking it down into 6 repeatable steps, you're making the process much more approachable by anyone in a production facility, whether that be operations, engineering, or maintenance. So I think those remarks were spot on. Thank you, Brett. Vera, why don't you advance to the next slide?
Yeah, thank you so much for this webinar. It was very informative and helpful. I will launch the last poll.
Great.
It's more about how can we contact you if you need some informations. We have a PID tuning guide, the upcoming workshops for PID tuning best practice, the upcoming webinars, control loops audits and process optimizations. How can we help you with the software Loop Pro PID tuning? So let us know. And then we will go to the questions.
If I could comment, Vera, the tuning guide is a great document just to save to your desktop. Offers a thoughtful series of remarks and visual guides for breaking down the tuning process. It's something that we cover in training workshops here for understanding process dynamics before diving in with bump test recommendations and whatnot. Very, very helpful resource that I encourage anybody who does tune loops to download.
Sure, here there is no right questions. You can apply everyone that you want to for us to be in contact with you. I think it's done. Let's go to the questions. So Brett and Dennis, again, thank you. There is a question here on the slide showing industries where PID loops are used. Where would water and wastewater rank?
That's a great question. In fact, Brett, I think you have some unique perspective given your days with 3M Cuno. But I think a general observation about water wastewater is the complexity of a lot of those processes is such that it doesn't demand a high number of PIDs, but it doesn't suggest that the importance of those PIDs are insignificant.
Right, I don't have the percentage off the top of my head, but you've got the situation where, especially with if you have like wastewater treatment where you have really long dead times, a lot of times those will be implemented with PID, but then augmented with perhaps a feed forward strategy or things of that nature. You know, there's a lot of just sitting around and waiting when you're talking about wastewater treatment in particular. I don't have the number off the top of my head, but I would say that it's lower than these others. We may have people from that may be the camp of people that tune loops infrequently, but still, you'll have a PID loop probably on chemical dosing and things of that nature. And that's a place where you kind of want to not overshoot, right? For either regulatory or for just cost reasons, right? Why add more chemical if you don't want to pay for it, right? So these are things that, and also with these long dead times, I mean, sometimes we're talking like an hour for it to get through the treatment. And so it can be very difficult to do multiple tests manually. Anyway, the answer is I'm not exactly sure the percentage, but I can speak to specific processes where there are PIDs, and man, getting those dialed in as few tries as possible is really going to be helpful to the bottom line.
Thank you. What types of savings has Control Station observed when applying this knowledge?
Right, I'll start with that. I think we can all appreciate that in a typical production facility, there's not one PID control loop, but rather there are large quantities. In water, wastewater, it might be dozens of PIDs, but in oil and gas, it may be thousands of PIDs. So oftentimes we see some challenge with the calculation of benefit and attributing it to one PID that gets tuned. That notwithstanding, we've seen a wide range of success. I'm thinking of chemical reactions where the settling time by tuning one controller was reduced by 15 to 20%, which meant they could produce that many more batches in a given day or other period. And the return on investment there is probably counted in very significant values. I'm also thinking of a recent customer who said that by tuning PIDs across their enterprise, they were able to save tens of millions. But of course, that's looking at optimization of all of the PIDs. So there's significant benefit. We're seeing, and we publish statistics that offer a perspective of savings of 2 to 5% on production inputs. We're seeing 5 to 10%, actually even greater in terms of reducing energy consumption. We're seeing 25% in reduction of defects. So there's any number of different ways to quantify, to calculate the ROI of PID, but that will typically be industry specific, even facility specific.
Yeah, I would add to that. Yeah, I would add to that. And that's one of the reasons that we focus on the time savings, right? Because that one is, it's one of those things where just the time savings alone, which is very easy to understand, is going to be beneficial, right? And then you have just the fact that you're going to do it. So these are the reasons that we kind of talk about those things primarily, initially, just because beyond that, there's then the actual process savings about usage of chemicals or operating more closely to constraints or not getting docked for a regulatory infraction. All of those things are gravy, but they're very specific to individual industries. And so here in a generic stance, just the time savings alone by being able to tune 5 loops in the time it used to take you to tune 1 loop just is also a good thing to look at when it comes to saving money, because
and maybe to put a fine point on that, Brett, so I'm glad you brought that up. The time savings can be taken from days or even a week, the tuning of 1 loop down to hours, and that is a common remark shared by many of our customers who utilize our PID tuning software, Loop Pro. Our next question.
Yeah, so have you seen in the area of maintenance, like overly aggressive tuning causing excessive movements on valves when not needed?
Oh yeah. Yes. So one that jumps to mind is that a new maintenance engineer increased the derivative on a loop to get it to control more tightly, but in doing so created a lot of valve chatter in one specific area where it was operating, and then it turned out that they wore the valve stem in that area, which meant that whenever the process needed to cross through that area, it would stick. So yes, you can ruin things with bad tunings. That is that experience jumps to mind. But that, yes, but even just more so, if your controller is more aggressive than it needs to be, you are just going to have more full strokes. The actuator is rated for a certain number of full strokes, and it will need to be replaced sooner just because of that. That would be my answer to that one.
Thank you, Brett. Another one here. What are some of the factors to consider when tuning for different applications, like consistent flow out of a buffer tank versus maintaining a perfect level set point?
Right. Okay. So that is really the balance between aggression and being conservative. The process is exactly the same, but it's really about dialing in that closed loop time closed loop time constant. I would also add considerations such as you have two loops right next to each other and they'll fight if they're tuned to the same speed. You can dial one back to make it more slow so that they don't interfere with each other. There are many considerations, but they can all really be approached with this kind of, do I want it to be fast? Do I want it to be slow? An additional consideration you might have there is, how am I going to perform my tests? Because you want to make sure that your tests are indicative of the real process conditions. And so if you have fighting between valves and things like that, those are also going to be considerations that you want to include in the first step, which is, what am I even trying to accomplish here? I would say that the two most difficult parts would be that step, and then sometimes finding a spot, so I would say that yes, defining the control objective and getting the data would be the most kind of time consuming parts of the process, just because of that, because there are various things that you want to consider.
Thank you, Brett. I think we have time to one more. So what are other examples of challenge that can be addressed through tuning software?
It's an interesting question. Other challenges. I think, Brett, one thing that you're an expert on is the modeling that results from PID tuning, and whether that be the eliminating the need for a steady state condition, or the ability to examine the subsequent model and make refinements based on what is visible through the third-party software like LoopPro. Care to comment on those two?
Sure. Yeah, being able to model quickly is certainly one of the things that helps. And also just some of the challenges that you might be able to deal with software is that if you have a loop that's so poorly controlled or so unsafe that you can't put it in automatic, you can't put it in manual because it'll just go flying out of control. Being able to have software to be able to model things and then kind of use that to temper the process to then model it again to make it even more safe. This is another thing where having a procedure in place and having software in place can really help with that procedure in a way that would be kind of scary to do by hand.
I'll come back to the idea of non-steady state modeling. Whether manual methods or other third-party software products, they all require, before initiating a bump test, they require an individual to first steady out the process before, again, initiating the test. And one thing that LoopPro from Control Station does is it eliminates that requirement. Brett actually is the brilliant mind behind that innovation here at Control Station. So you can have noisy oscillatory data, and rather than spending the time, the effort, stabilizing or steadying it out, you can just go right into your bump test, go outside the noise band, fit your model, and begin calculation of tuning correlations. And I think that that is a significant advantage of tuning software, specifically Loop Pro, over manual methods. It's a big time savings.
Back to that time savings.
There is one interesting question here. Do you have any loop monitoring software?
Yes.
That's a loaded question. Brett, why don't you jump in on that?
Sure, yeah. Loop monitoring. Yeah, no, we have Planet ESP. We've had it for many years. So that would be, we're talking about statistics earlier on to kind of monitor and determine whether the control loop is degrading. That's the topic of a separate webinar. But yes, we have a supervisory monitoring package, control loop performance monitoring package that will run 24 hours a day, analyzing loops to determine if performance is degrading, if valves are sticking, if tunings are deviating from where we think they should be, and kind of gives you the peace of mind that once you fix something, it will stay fixed, or we will notify you if it starts to degrade from its improved state.
Seems very fitting that we're seeing Lindsay of Seek here as we're handling this question. Technologies, control loop performance monitoring tools like Plant ESP perform that proactive analysis of a facility's continuous process data. And again, it proactively is the key word here, identifies those controllers that are showing signs of degraded performance, and then ultimately characterizing the changes, whether they be an issue with tuning or loop interaction or a mechanical issue even. And again, that is something that Lindsay will dive into with Dr. Bob Rice next month. And hopefully whoever posed the question will join us for that informative webinar. Any other questions there, Vera?
Let's go to the last one. We have 3 minutes to close the webinar. So what is the best type of pump test to use?
This is a question wired for you.
It depends, right? Generally, if I have to pick, I'll do something called a doublet test, where we want to get process dynamics. And so rather than do a large bump away from where we're operating, I'll go up by a little bit, then down across, and then come back. That lets us kind of get good data above and below where we're operating. But that's kind of a personal preference. The nice thing about using software is that you can do a variety of different tests and still generate process dynamics. So for example, if you're operating very close to a limit and you don't want to cross that limit, you can do a bump test that only goes down and comes back up. Perfectly fine. Again, it's more of a preferential thing based on where you're operating. The real key is that you want to step on the gas and see how your process responds, right? That's the key. You can't sit there and wait for some external disturbance to hit you and you react, because then you can't really separate what's your process and what's the disturbance. But other than you driving the ship, there's no right answer. There are a variety of different tests that can still yield good data.
As the non-engineer here, I'll chime in that I too conceptually like the doublet, the idea of moving up, but then also moving below set point, revealing the potential differences in behavior. If you think temperature loop, heating is different than cooling. And so you may, through that doublet, explore different and even competing dynamic behavior and establish tuning parameters that accommodate both aspects of a process's dynamics.
Thank you so much. There is just one question here, but it's about the recording. This webinar is recorded, so just be in touch with us and we can send the recording. And I want to thank you all to coming here, to watching until the end, and thank you very much. I hope you have a great week. Thank you, Dennis and Brett. It was really great.
Thank you, Vera. Thank you, Brett. And thanks everyone who joined us today.
Thank you.